Okay, so today we're going to talk about two-way ANOVA and analysis of covariance, or ANCOVA. So let's first talk about two-way ANOVA. Okay, so up to this point, we've talked about ANOVA and repeated measures ANOVA. And we use these when we have a quantitative outcome or dependent variable and a single categorical independent variable, which we've referred to as a factor. So for ANOVA, we might be interested in looking to see whether BMI, or our outcome or dependent variable, varies by race and ethnicity. And these are just our categories of race and ethnicity, so white, Black, Hispanic, Asian, and other. For repeated measures of ANOVA, we might be interested in BMI. So again, that's our outcome or dependent variable across 3 or more time points. So before, during, and after an exercise program. So all of these measures are within the same individuals. Or for example, we might be interested in looking at 3 or more treatment groups. So no music, classical music, or rock music during exercise, where all individuals are rotated through all 3 treatments. One-way ANOVA, however, is limited. So far, our ANOVA problems have only one dependent variable. So in our previous example, it was BMI, and we have one independent variable. So for example, what if we wanted to examine hours of weekly exercise by relationship status and race and ethnicity? So if we wanted to look at the hours of weekly exercise by relationship status, and let's say we have 3 levels here, single, dating, and committed relationship, we would conduct a one-way ANOVA. And then if we wanted to look at hours of weekly exercise by race and ethnicity, we would have to conduct a second one-way ANOVA. But this is limited because it doesn't really tell us if there's a connection between race and ethnicity and relationship status on hours of weekly exercise. So it really can only tell us the independent relationship or connection between each of those factors and our outcome variable, but it doesn't tell us how the two relate to each other. So again, a two-way analysis of variance examines the case of 2 independent categorical variables. And the process would be the same for a larger number of independent variables. So we can have a 3-way analysis of variance or more. And again, we can use it to examine the effect of the 2 independent variables on our dependent variable. So from our example, we're looking at factor 1 is our relationship status. And looking at the effect or connection with a dependent variable, hours of working out. And then our second factor is race and ethnicity. In a two-way ANOVA, the effects of these 2 factors can be investigated simultaneously. So that is in contrast to having to conduct 2 separate one-way ANOVAs. So the two-way ANOVA permits the investigation of the effects of either factor alone. So in another example, we might be interested in the effect of training intensities on strength and the effect of humidity on strength. And we can also look at the 2 factors together. So the combined effect of training intensity and humidity on strength. So this ability to look at factors together is a major advantage of a two-way ANOVA compared to having to conduct 2 separate one-way ANOVAs. So why use a two-way ANOVA? It is just an extension of a one-way ANOVA. So let's say for this example of looking at strength, and we're interested in investigating the effect of training. And in this case, we have 2 levels, so 2 different intensities and weather. And in this case, we have 3 levels, so 3 different conditions, weather conditions. And we're looking at those effects on muscular strength. So if we were to conduct one-way ANOVAs, it would require us to look at 6 different one-way ANOVAs to investigate this, instead of just using one two-way ANOVA. So what we're doing here is we're looking at whether the effect of different training intensities on muscular strength is the same in each weather condition, And then we're also looking at whether the effect of different weather conditions on muscular strength is the same in each training intensity. But we can't investigate the interaction between these two, between training intensities and weather. So that's where we would conduct a two-way ANOVA experiment. And then this way we can look at each of those individual effects as well as the interaction between our two independent variables. And in this way, we're utilizing more data and resources more economically. So for example, our focus for a study like this might be that we want to investigate which treatment combination is most effective. So we have several assumptions when we conduct a two-way ANOVA. The population from which the samples have been drawn must be normally distributed. We assume that we have two independent variables that are categorical, and that we have one dependent variable or outcome variable that is an interval or ratio variable. The samples must be independent. The population variances must be equal, and there shouldn't be significant outliers in the data. And these are things that we check for, right, in our data before we run our analyses. So we have several hypotheses actually for a two-way ANOVA. So we're really asking three questions when we conduct a two-way ANOVA. The first is there any effect of factor A on the outcome? And we refer to that as the main effect of A. The second question is there any effect of factor B on the outcome? And we refer to that as the main effect of B. And then finally, we're asking, is there an interaction between the two factors? So our statistical hypotheses look like this, okay? And we have three sets of hypotheses. So for the main effect of A, we're saying that the means for all of the levels of factor A are equal, and they're all equal to 0. And the alternative hypothesis is that they're not all equal to 0. When we're looking at the main effect of factor B, our null hypothesis is that the means for all of the levels of B are equal to 0. And then our alternative hypothesis is that not all of them are equal to 0. And then for our final set of hypotheses, when we're looking at interaction, the null hypothesis is that there's no interaction between factor A and B. And our alternative hypothesis is that there is an interaction between factor A and B. So what does that mean? What is an interaction? An interaction between the two variables just means that the effect of one of these variables on the outcome or the dependent variable is not constant. In other words, the effect differs at different values of the other. So you can see on the top half, so this figure and this figure, you can see that values of A look very different, right? So values of A at level 1 are very different for each level of B when compared to level, the second category of A. Okay, so you can see where they actually diverge from each other. And then the same thing here, where the value of A level 1 at level 1 is quite high for level 1 for the variable B, and then it drops down when we have level 2 of B, and then it goes back up again for level 3 of B. And then we see actually quite the opposite happening, right? For level 2 of A, it's quite low for the first level of B, and then it increases and is quite high for the second level of B, and then it decreases. In contrast, we can see that for level 1 of A, there's sort of a consistent increase, much like we see here. However, for level 2, we see a parallel increase. So the slopes are pretty equal here. So even though the value of level 1 of A changes across levels of B, that change is consistent for level 2 of A as well. So when we see that the slopes are parallel here, we would conclude that there is no interaction. So that change is constant. And the same thing is happening here. So those slopes are parallel. So the change in A for level 1 of A is constant across levels of A. Okay, so let's give another example. So let's say a researcher wants to study the effect of practice on learning a novel throwing task. So let's say we have 2 groups of people. We have 9 athletes and 9 non-athletes. And then we further divide those groups. So each group is split into thirds. So we have 3 athletes and 3 non-athletes in each of these 3 groups. So low practice, moderate practice, and high practice. Just as an aside, we have the same number of subjects in each cell. So we have 3 individuals in the athlete low practice, athlete moderate practice, athlete high practice. And we also have 3 individuals in each cell. So for the non-athletes, so non-athletes low practice, non-athletes moderate practice, non-athletes high practice. And when we have the same number of subjects in each cell, we refer to this as a balanced sign. Okay, so another term for the 2A or more ANOVA is a factorial ANOVA. So factor A is our athletic experience, so our athlete or non-athlete categories. And then factor B is our training volume. So we had our low, moderate, and high training volume. So 1 day a week, 3 days a week, 5 days a week. Our interaction, we can also look at the interaction between factor A and factor B. So whether the effect on throwing accuracy differs for athletes versus non-athletes across levels of training volume or vice versa. And that would be looking at our interaction between factor A and factor B. So again, 2 factors interact when the differences between the mean values on one factor depends or differs upon the level of the other factor. So again, we saw visually, there's an interaction when the slopes of the lines describing the effects of the 2 factors are different. So the magnitudes can be different, but if the slopes are different, then there is an interaction. So this is just another visual showing that there is an interaction between our athlete experience, so our athletes and non-athletes, and the frequency of practice on the outcome, which is our throwing accuracy. And we can see this here in our output, and we're gonna run an, actually just a one-way ANOVA for exercise 2 on Tuesday. But you can see here, so this would be the main effect of experience, the main effect of practice, and then the interaction between experience and practice. And if we work our way over here to the p-value, we see that it's less than 0.05. So remember, our null hypothesis is that there is no interaction between factor A and factor B. Because this p-value is less than 0.05, we reject the null hypothesis in favor of the alternative hypothesis, which state that there is an interaction. I'll emphasize it again later, but if there is an interaction, a significant interaction, then we can no longer interpret the main effects just like this in our model. We have to now take into account that there is an interaction between these 2 values. Okay, so just like what we saw on the previous slide, when we looked at the interaction term for experience and practice, our p-value is 0.016, so it's less than 5. So what we would conclude, less than 0.05. So what we would conclude is that the effects of practice differed based on experience, and that the effects of experience differed based on practice. For factor A, we saw that the p-value is 0.001. So the score differed between experience levels independent of practice. For factor B, we saw that the p-value was less than 0.001, so we can conclude that the score differed with practice independent of experience. Okay, so remember, if the interaction is significant, we cannot interpret the main effects. And I'm going to emphasize this again because this is really, really important. So a lot of times in our output, we will have, coefficient estimates, coefficients or beta estimates. If our interaction is significant, then we cannot interpret our main effects for factor A and factor B in the given output, because the interaction indicates that the effect of one independent variable has on the dependent variable is based on levels of the other independent variable. So when we find that we have a significant interaction, then we need to run simple main effects models. So a main effect model just means that we have a model without our interaction term, or we need to run the appropriate interaction contrasts to then get the appropriate main effects values, taking into account that interaction. So this is a very, very busy slide, and I'll go through it. It's just to kind of introduce, again, like the sum of squares and how we're dividing up the variance. But I think what's going to be more important is if we then tie this in our exercises. So when we look at the output, which selection to make. So let me just go through this. All right, so we have 3 different types of sum of squares. So in our type 1 sum of squares, and this is referred to as the sequential sum of squares, and I put here order matters. So the order in which we put our variables, our independent variables, our factor A and factor B, does matter. So we have the sum of squares for factor A, that's our main effect of factor A. And then order matters here because what the model is doing is it's giving most of the variance to A, and then whatever is left over, it's now looking at B. So we have then the sum of squares for B, for factor B, and that's the main effect of factor B after the main effect of A. And then finally, we have the interaction for A and B, and that's after the main effects. Excuse me. For type 2 sum of squares, this is used when interaction is not statistically significant. And in this case, order doesn't matter. So we have the sum of squares for factor A, and this is just the main effect of factor A after the main effect of B. And then it's just the reversal. So sum of squares for factor B is the main effect of factor B after the main effect of A. And then finally, we have interaction for AB. But we only use this type 2 if the interaction AB is not significant. Finally, if our interaction term is significant, then we would look at our type 3 sum of squares. So our sum of squares for factor A, and then our sum of squares for factor B. And this is the main effect of A after the main effect of B and the interaction. And then likewise, the main effect of B after the main effect of A and the interaction. So just remember, like if there's a statistically significant interaction between the factors, then we have to take into account that interaction when we're determining the main effects of each of those individual factors. And then just a note here, don't confuse these sum of squares with type 1 error. So remember, type 1 error refers to rejecting a null hypothesis when it is actually true or a false positive, or type 2 error, which is failing to reject the null hypothesis when it is actually false, so a false negative. Okay, so that's different. So these are different. These type 1, type 2, and type 3 sum of squares are different from our type 1 and type 2 errors. What about a two-way repeated measures design? So We would use a two-way repeated measures ANOVA if we have a study, for example, that has measured a dependent variable over time when all subjects have gone through 2 or more trials or treatments. So a two-way repeated measures ANOVA can be run when we've measured any 2 within subject factors and want to understand if there's an interaction between those factors. This is similar to a two-way mixed ANOVA, which we'll talk about later on next week, where subjects are measured over time, but there are different subjects in each trial or treatment. So there's one within factor, right? So all subjects are measured over time, and then there's one between factors. So there are different subjects in each trial or treatment. If you're interested, okay, so here's an example for when we would use a two-way repeated measures ANOVA. So let's say we're interested in determining whether a short-term, high-intensity exercise training program can reduce a marker of heart disease and called C-reactive protein. And that's just an inflammation, a marker of inflammation. So for example, our question might be, can a 2-week training program reduce C-reactive protein? So let's say we have 12 participants and all 12 participants complete 2 treatments, a control and an intervention. In the control, participants continue their normal activities, and in the intervention, they exercise for 45 minutes a day. And then we measured their C-reactive protein at baseline, so at the start of the study, at the midpoint of the study, and at the end of the study. So we have 3 time points. So in this two-way repeated measures ANOVA, our dependent variable is C-reactive protein, and then we have 2 within subjects factors, time and treatment. Okay, so what if the interaction is significant? Then we need to run separate ANOVAs. So in this case, we would run 3 one-way ANOVAs for each level of time. So baseline, midpoint at the end of the study, and then 2 one-way ANOVAs for each level of treatment. So control, and then the intervention, the exercise intervention. Okay, and then let's talk about analysis of covariance. And I know this is, I know it's getting confusing. So, you know, we're still going to talk about additional types of ANOVA next week. And then once I do that, I'll try to tie it all in together into a single slide, and hopefully it will make sense when you see it all tied in together. So bear with me. We're almost there. All right. So if you have a model where you have no continuous factors, so you just have categorical factors, then we would use an ANOVA. We refer to this as an ANOVA. If we have a model with no categorical factors, then we refer to this as a regression. But what if you have a model that has both continuous and categorical factors? Then we would be using analysis of covariance. So analysis of covariance, or ANCOVA, examines differences in a dependent variable, or our outcome variable, by both a factor and a continuous independent variable. So we're interested in the effect of the factor on our dependent variable, and we refer to this continuous independent variable as our covariate. So it's historically also been referred to as sort of like a nuisance variable. So here is just diagrammatically, we have our factor, and in this example, we have an intervention. So we have high intensity interval training, running, and a control group. And then we have our covariate, which is caloric intake. And we're looking at our outcome variable or dependent variable, and that's body fat percentage. So what are the advantages of ANCOVA? So again, we can test for differences between group means when we know that there's some extraneous variable that affects the outcome variable. And so we can use ANCOVA to control for this extraneous variable, and we refer to them as confounders. So for example, in a pre-post study design, we can determine changes in an outcome by levels of an intervention, taking into account pre-intervention scores. ANCOVA reduces error variance by explaining some of the unexplained variance or the residual sum of squares And then there's greater experimental control. So we can control for these known extraneous variables or confounders or covariates, and that provides greater insight into the effect of the predictor variables because we're controlling for the effect of these other extraneous variables. It's kind of a cleaner look at these predictor variables. So the hypothesis for ANCOVA is that there's no significant effect of factor A on Y controlling for the covariate. And then our alternative hypothesis is that there is a significant effect of factor A on Y controlling for the covariate. With ANCOVA, we can also test the hypothesis that the covariate is significantly associated with the outcome as well. So let's look at it as a regression. And this should say ANCOVA up here in the header. I'll change that before I output these as PDF slides and post it onto Cougar Courses. So ANCOVA by definition is just a general linear model that includes both categorical predictors and continuous predictors. So we could run a regression with body fat percent as the outcome and exercise intervention as the predictor, and then we would just add the covariate caloric intake to the regression model. To evaluate the effect of the experimental manipulation controlling for the covariate, we would enter the covariate into the model. We say here, let's say X is for the intervention, and then we have our covariate here. And then this would just be body fat percent. So how would we report the main effects once we run our model? We would say there was a significant effect on the intervention on body fat percent. So P was less than 0.05, and then we report our R after controlling for the effect of caloric intake. In post-hoc analyses, mean body fat percent was XX percent among those in the high intensity interval training group compared to XX percent in the control group and XX percent in the running group. And that all differences were significantly different. So all p-values were less than 0.05. And then we might go on to say there was no significant difference in body fat percent in the running group compared to the HIIT group. So this is just an example of how we might report our main effects for a study like this. And that's actually all I had. So I've tried to keep it short because I know that these ANOVAs are maybe a little bit hard to digest, but I'm hoping that after next week and tying it all together in our live lecture after we've discussed the remaining types of ANOVA that we'll discuss in this course, it'll all come together. So I will see you on Tuesday. We'll have like a quick summary lecture, and then we'll just dive right into exercise 2. I would ask you if you please, if you haven't already, go back into the R program for exercise 2, merge all of those NHANES data sets like we did on Tuesday, and then save that R object as an R data set, and then please import it or load it into your working environment before the start of class on Tuesday. And then that way we can just all start together after the summary. Then we can just dive right into exercise 2. And please email me if you have any issues doing that. I'm happy to help you out.